In Chapter 5, Section 1, we will discuss probability distributions. A probability distribution tells you what the probability of an event happening is. Probability distributions can show simple events like tossing a coin or picking a card, or they can show much more complex events like the probability of a certain drug successfully treating cancer. In this section, we will be introduced to the concept of a random variable and the concept of a probability distribution. We will illustrate how a probability histogram is a graph that visually depicts a probability distribution. We will also show how to find the important parameters of the mean, standard deviation, and variance for a probability distribution. And most importantly, we will describe how to determine whether outcomes are significant, either significantly low or significantly high. A random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. We could also say that a random variable is numerical in the same way that x is numerical, except it is attached to a random event. Let's take rolling a die, for example. It's a random event, but you can quantify it. You can quantify the outcomes. Let's say you wanted to know how many sixes you get if you roll the die a certain number of times. In this case, your random variable x could be equal to 1 if you roll a 6, and it could be equal to 0 if you get any other number other than 6. A probability distribution is a description that gives the probability for each value of the random variable. It is often expressed in the format of a table, a formula, or a graph. We can also say that a probability distribution describes the dispersion of the values of a random variable. A discrete random variable has a collection of values that are finite or countable. If there are infinitely many values, the number of values is countable if it is possible to count them individually, such as the number of tosses of a coin before getting heads. Other examples of a discrete random variable include the values obtained from rolling a die or the grades received on a test out of 10 points. A continuous random variable has infinitely many values, and the collection of values are not countable. That is to say, it's impossible to count the individual items because at least some of them are on a continuous scale, such as weight or body temperature or distance. Every probability must satisfy each of the following 3 requirements. First, there is a numerical, not a categorical, but a numerical random variable x, and its number values are associated with corresponding probabilities. Second, the sum of those probabilities, all of those possible probabilities, is equal to 1, where x assumes all possible values. The sum of all probabilities must be 1, but sometimes the sums will equal to 0.999 or 1.001 due to rounding errors, and these are acceptable results. The third requirement is that every probability of x will be between 0 and 1. That is to say, 0 is less than or equal to the probability of x is less than or equal to 1 for every individual value of the random variable x. Let's consider an example where we're tossing 2 coins with the following random variable, where x equals to the number of heads when we toss our 2 coins. Here we say that x is a random variable because its numerical values depend on chance. When we toss 2 coins, we have 4 possible outcomes when we're looking at the number of heads. One outcome would be 0 heads, where we would have 2 tails. So the probability of 0 heads would be 1 out of 4, which would be 0.25. Another possibility would be to toss 1 head. Well, there's 2 possible ways we can get 1 head. You can get a head and a tail, or a tail and a head. So the probability of getting 1 head is 2 out of 4, which is equal to 0.50. And finally, the probability of getting 2 heads, your toss would be a head and a head, and there's only one possible outcome for this, and that's a head and a head. So the probability of getting 2 heads is equal to 1 over 4, which is equal to 0.25. With the 2 coins tossed, the number of heads can be either 0 or 1 head or 2 heads, and the table is the probability distribution because it gives the probability for each value of the random variable x, and it satisfies the 3 requirements we mentioned earlier. The first requirement is that the variable x is a numerical variable, and it is associated with probabilities. Second, the sum of those probabilities is equal to 1 because we know the probability of 0 heads is equal to 0.25, the probability of 1 head is equal to 0.5, and the probability of 2 heads is equal to 0.25. When we sum those up, we get 1. And finally, each value of the probability of x is between 0 and 1 inclusive. In our coin toss example, the random variable x in the table is a discrete random variable because it has only 3 possible values that we can count, 0, 1, or 2. And the 3 possible values are a finite number. So this satisfies the requirement of being finite. A probability histogram is similar to a relative frequency histogram, but the vertical scale shows probabilities instead of a relative frequency based on the actual sample results. This histogram is the probability histogram for the number of heads when two coins are tossed. Notice that our y-axis, or our vertical axis, displays numbers between 0 and 1, and the x-axis, or our horizontal axis, displays the possible outcomes of our discrete random variable x. A probability distribution could also be in the form of a formula. Let's consider the formula. The probability of x is equal to 1 over 2 times 2 minus 1 factorial times x factorial, where x can be either 0, 1, or 2. So we find that the probability of 0, when we plug in 0 into our equation, is equal to 0.25. The probability of x equal to 1 will be equal to 0.5, and the probability of x equal to 2 is equal to 0.25. So the probabilities found using this formula are the same as those in the table that we displayed previously. Let's consider another example. In this example, hiring managers were asked to identify the biggest mistakes that job applicants can make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution? The table violates the first requirement because x is not a numerical random variable. The values of x are categorical in this example. They're not numbers. It also violates the second requirement because the sum of the probabilities is equal to 1.57. They really should equal to 1 to meet the requirements. Because the 3 requirements are not all satisfied, we would conclude that this table does not describe a probability distribution. Remember that with a probability distribution, we have a description of a population instead of a sample, so that the values of the mean, the standard deviation, and variance are all parameters and not statistics. The mean, variance, and standard deviation of a discrete probability distribution can be found with the following formulas. The population mean mu for a probability distribution is equal to the mean equals to the sum of the x values multiplied by the probability of x. One formula for variance is variance, which is sigma square for a probability distribution, is equal to sigma square equals to the sum of x minus the population mean quantity squared multiplied by the probability of x. This formula is easier to understand. Another formula for the variance is for a probability distribution is sigma square equals to the sum of x squared multiplied by the probability of x minus the mean squared. This format is easier to calculate by hand. And finally, the standard deviation, or sigma, for the probability distribution is sigma is equal to the square root of the sum of x squared multiplied by the probability of x minus the population mean squared. The expected value of a discrete random variable x is denoted by the capital letter E, and it's the mean value of the outcomes. So the expected value equals to the population mean. And the expected value can be found by evaluating that formula of the sum of x times the probability of x. The expected value is exactly what you think it might mean intuitively. That is to say, the return you can expect from some kind of action. For example, how many questions might you expect to get right if you're guessing on a multiple choice test? This table describes the probability distribution for the number of heads when you're tossing two coins. Let's find the mean, variance, and standard deviation for this probability distribution. This table will help us calculate our mean, variance, and standard deviation for our probability distribution. The two columns at the left describe the probability distribution, and the two columns at the right are for the purpose of calculating our mean, variance, and standard deviation. So you can see from the third column we can get every element we need for the mean of our probability distribution. We take the value of x and multiply it by the probability of x, and we do that for each of our possible outcomes of x. We sum it up, and that gives us our mean value for x. And in this case, it is equal to 1. The last column on the right shows us the steps to calculate the variance of our probability distribution. We take the value of x, subtract the mean, square that, multiply by the probability for each row in our probability distribution, sum up those values, and that gives us the variance of our probability distribution. In this case, that is equal to 0.5. And finally, we can calculate our standard deviation for our probability distribution by simply finding the square root of our variance, which we've already calculated. Recall our variance was equal to 0.5. So the square root of 0.5 is equal to 0.707107, or approximately equal to 0.7. So we can interpret this in the following way. When tossing two coins, the mean number of heads will equal to 1.0 heads. The variance is equal to 0.5 heads squared, and the standard deviation is equal to 0.7 heads. Also, the expected value for the number of heads when tossing 2 coins is equal to 1 head, which is the same value as the mean. If we were to collect data on a large number of trials with the 2 coins tossed in each trial, we'd expect to get a mean number of 1 head. Recall that the range rule of thumb is a simple tool for understanding and interpreting standard deviation. It is based on the principle that for many datasets, the vast majority of sample values lie within 2 standard deviations of the mean, and is based on the population mean mu and the population standard deviation sigma. This rule applies to large samples that represent the population. So we could say that significantly low values would be any value that is the population mean minus 2 standard deviations or lower. Significantly high values would be any value that is the population mean plus 2 standard deviations or higher. And finally, values are not significant would be any value that is between the population mean minus 2 standard deviations and the population mean plus 2 standard deviations. Let's consider this example. We found that when tossing 2 coins, the mean number of heads is equal to 1 head and the standard deviation is equal to 0.7 head. Use those results and find the range rule of thumb to determine whether 2 heads is a significantly high number of heads. Using the range rule of thumb, the outcome of 2 heads would be significantly high if it's greater than or equal to mu plus 2 sigma. Recall that our population mean mu is equal to 1 head, and our standard deviation sigma is equal to 0.7 head. And when we plug those numbers into our range rule of thumb equation, we get that the population mean mu plus 2 sigma is equal to 1 plus 2 times 0.7. This gives us 2.4 heads. So a significantly high number of heads would be 2.4 heads or above. And so based on these results, we can conclude that 2 heads is not a significantly high number of heads. This is because 2 is not greater than or equal to 2.4. We could define a significantly high number of successes as follows. We could say X successes among N trials is a significantly high number of successes if the probability of X or more successes is equal to 0.05 or less. The value 0.05 is not an absolute rigid value. Other values such as 0.01 could be used to distinguish between results that are significant and those that are not significant. A significantly low number of values can be described as follows. X successes among N trials is a significantly low number of successes if the probability of X or fewer successes is equal to 0.05 or less. Again, the value of 0.05 is not absolutely rigid. Other values such as 0.01 could be used to distinguish between the results that are significant and those that are not significant. If, under a given assumption, the probability of a particular outcome is very small, and the outcome occurs significantly less or significantly greater than what we expect with the assumption, we can conclude that the assumption is probably not correct. Recall that the expected value of a random variable X is equal to the population mean mu. We can therefore find the expected value by computing the equation, the sum of X times the probability of X, just as we do when we're finding the population mean mu. Let's consider this example. You have $5 to place on a bet at the Golden Nugget Casino in Las Vegas, and you've narrowed down your choices to one of two bets. The first bet, you might bet on the number 7 at the roulette wheel, or you could bet on the pass line in the dice game of craps at the craps table. If you bet $5 on the number 7 at the roulette wheel, the probability of losing your $5 is 37 out of 38, and the probability of making a net gain of $175 is 1 out of 38. This is because the prize would be $180, and so including your $5 bet, your net gain would be $175. So let's find the expected value if you bet $5 on the number 7 at the roulette wheel. Or if you bet $5 on the pass line in the dice game of craps, the probability of losing your $5 is 251 out of 495, and the probability of making a net gain of $5 is 244 out of 495. So if you bet $5 on the pass line and you win, you're given $10, and so that includes your bet, so your net gain is $5. So let's find our expected value if you bet $5 on the pass line. Which of these two bets is better in the sense of producing higher expected value? The probabilities and payoff for betting $5 on the number 7 at the roulette wheel are summarized in this table. So from this table we can see that the expected value is a negative 26 cents. In other words, for every $5 you bet on the number 7, you can expect to lose on average 26 cents. For the craps game, the probability and payoff for betting $5 on the pass line in craps is summarized in this table. The table shows that the expected value is negative 7 cents. So that is to say, for every $5 bet on the pass line, you can expect to lose on average 7 cents. The $5 bet at the roulette wheel results in an expected value of a loss of 26 cents, and the $5 bet in the craps table results in a loss of 7 cents. Because you're better off losing only 7 cents instead of losing 26 cents, the craps game is better in the long run, even though at the roulette wheel you will have a greater opportunity for a larger payoff when playing the game just one time. This is the end of Chapter 5, Section 1. Please proceed to Chapter 5, Section 2.